Hello everyone. Today we are going to talk about the most talked algorithm in the graph theory, that is Dijkstra's algorithm, and it is the algorithm that is responsible for finding shortest paths from the source to a given destination. But before we get started, make sure you check out free masterclasses on Scalar's event page to learn from some of the best industry experts. The link is in the description below. Alright, let's dive right into the tutorial. So what is Dijkstra's algorithm? It is an algorithm for finding shortest paths between nodes in a weighted graph, which may represent, for example, road networks. For example, you're traveling through a cab and you want to find out what is the shortest path to reach some X city. And this is where Dijkstra's algorithm will come into picture. So it was invented by computer scientist Dijkstra in 1956, and it has many other applications as well. This algorithm actually exists in many variants, and the original algorithm found out the shortest path between two given nodes, but we will do a more common variant in which we will build this algorithm as a single source shortest path algorithm. That means starting from a single source, it will find out the shortest path to all other nodes in the graph, thus producing a shortest path tree. So input of this algorithm will be a weighted graph and a given source node. And once you have this as input, let's say the source node is A, the goal of this algorithm would be to find out what is the minimum distance in which I can reach every other node of the graph, right? So for example, what would be the minimum distance to reach B, D, F, E, and C, right? So in the beginning, we can say, okay, the source is at 0 and we want to compute the shortest distances to all other nodes. So this is what we will do in this algorithm. That is why it is called as single source shortest path. So we will be doing this. Starting from a single source, we will be finding out shortest path to all other nodes in a weighted graph. That is important, right? So if the graph is not weighted, if it is an unweighted graph, then we have already seen that a simple BFS can give us that thing. But if the graph edges are weighted, then this is where Dijkstra's algorithm will come into picture. So let us go and build this algorithm, try to understand the intuition and the logic of this algorithm. Let's see how this algorithm works. So we will start from the given source node. So let's assume that we are given this weighted graph and we are given, okay, the source node is, let's say, A, right? It can be any node, but I am assuming in my scenario the source node is A. What I will do, I will initialize the distance of the source node as 0 because this node is at distance 0 from itself. So what we are going to do, we are going to maintain a distance array and we are going to say, okay, there are different nodes A, B, C, D, E, F. So what this algorithm does, it initially gives a infinite distance to every node except source node. So all the nodes except the source node, they are not yet discovered. So they are at infinite distance. So that means they are not yet discovered. So B is at infinite distance, D is at infinite distance, E, C, and so. And distance of the source node is going to be 0, right? What do? You do something like BFS. Of course, will pick this node. Now, this node is having the minimum distance. Okay, so it makes sense. So out of all the edges, if you have to pick some edge, will you pick this edge B to D? The answer is no. Will you pick D to E? No, because D is at infinite distance, E is at infinite distance. So what is the first node you will pick? That node will be A. So this algorithm is also a greedy algorithm. So that means we will always make a choice that looks best at the moment. But at this moment, the choice that is looking best is A. So what I will do, I will pick A, okay, and I will try to cover the neighbors of A. The neighbors of A are B and they are C, right? Now, if I pick this edge, can I go from A to B? The answer is yes. If I pick this edge, the distance of B, which was infinity, now this distance will become 4. Yes or no? The answer is yes, it will become 4. The distance of B will be how much? So from A, I will update B, and of course I can take this edge and I will update C also. I will update C also. Okay, so distance of C, which was again infinity, it will be now 0 plus 5. That will be, this distance is 5, and in the array also we can update that this distance is 5. So what I did, I picked A and I put it in some data structure. Okay, so I have some data structure. I will tell you what this data structure would be, right? So we initially put A, and then we said, okay, we picked A from this data structure and we updated B and C. And now I want to do this step again, right? Now I cannot pick A, but I have to pick again something, right? Now I'm going to put B and C in this data structure. Why? Because B is at a distance 4, right? Okay. And I want to put C also. C is at a distance 5, right? These nodes are also inserted into the data structure. Now, one property of this data structure we would require is, since it is a greedy algorithm, we want this data structure to always give us a node with the minimum distance. So right now you see this node which is at the front of this data structure. Okay, so something like a min priority queue, right? Or something like a ordered set, right? This data structure can be min priority queue, it can be set also, right? Now what is the next node I'm going to pick? So A has done its work. I cannot traverse any other neighbors from A. So what I'm going to do now, I'm going to pick B. Okay, and of course B's distance cannot be minimized because I don't have any other node which is having distance less than B. So B cannot be minimized. So B is now having the minimum distance out of all the nodes that I have, right? So now it obviously makes sense to pick B. So that means B is now out. I cannot update B any further, and I can update the neighbors. So what are the neighbors? So one neighbor is C. So can I pick this edge? Can I travel this edge? If I go via this edge, you look at that. Okay, if I try to update C, the distance of C, which was 5, now it will become distance of B, that is 4 plus 11, 15. So it is increasing, so I do not update it. So I do not update C, right? Then I talk about this edge, B to D. So D was at infinite distance. Now the distance will be 4 plus 9, that is 13. So is it getting lesser? The answer is yes. So I updated. This distance is 13. Okay. So this distance of D is going to become 13. And of course, I'm going to push 13 comma D in my data structure. 13 comma D is in the data structure. What about this edge? Can I take this edge? The distance of E, it is how much? It was infinity. Now it is 4 plus 11. 4 plus 7, that is 11. Distance of E is also getting updated. So it was infinity. Now it is becoming 11. And I'm going to insert this into my data structure, right? So I want this to be in a way that is sorted according to distance, right? Because in future it might happen that from E to D there is an edge which is going to minimize this D, right? So we want to pop E first, right? So distance of E is actually how much? It is 11 comma E, right? So this distance infinity it should be 11, right? This should be 11. Now this should get inserted somewhere here, right? So let's say I now my data structure looks like this. So I have 5C followed by 11E followed by 13D, right? Something like this. Because B is now already out. This is how my data structure is going to look like. Now, next thing that I'm going to pop is I'm going to pop out C, because now all the nodes that I have traversed so far, this node is having minimum distance after A and B, and B has already visited this node, right? So we could not minimize this distance. That means C is at a minimum distance of 5. What I'm going to do, I'm going to now pick C, right? So we'll pick C and we'll try to update the neighbors, right? So neighbors which are not yet visited. So A and B, they are already out of the queue. So we will not update A and B. We might try to update C, E, right? From C I can go to E, right? So I can go to E. So E was at a distance 11. Now E is at a distance of 8. That means, yes, I need to update the distance of E because it is getting lesser. This distance will become 8, and now E is also in my data structure. E is also here, right? So if it is here, what should I do? I should update it, right? I should update it in the data structure also, right? Now, if you're using something like a min priority queue, right, then you do not have this update operation built inside priority queue, right? So instead of using a min priority queue, what we can do is we can use a set, right? Something like a tree set that keeps things ordered, right? In C++, you can use a set. In Java, you can use a tree set, right? This data structure will be set. Why? Because set also does not allow updation, but it allows you to remove and insert any element. So set allows you to do remove and then you insert, right? What I'm going to do, I'm going to remove this pair 11e. So this is already popped up because we have picked C. And now I want to update 11e, right? So I cannot update directly inside the set. What I can do is that e which was at 11 distance, I want to say this distance would be 8, right? So I'm going to remove this and I'm going to insert 8 comma. This is how I can update it in the set. And set it is an ordered set. 8 is lesser than 13, it will be present here, right? Then any other edge, no, I don't see any other edge, right? Now E, it is at distance 8, right? Now next node that you will pick is you will pick E, right? You will try to update the neighbors which are not yet covered. One neighbor of E is F. So F is at infinite distance. Now this distance will be 8 plus 6, that is 14. So F distance will be 14. So you can say, okay, F is now at distance 14. And of course you can put it into the set also, 14 comma F. So you took this edge. Then E can also visit D. D is not yet visited. So it will be now 8 plus this 13, right? So 8 plus 13, which is how much? Which is actually more. So you will not update D, right? So it is 21. So it's already 13. So you will not update it. That's it. So E is also done. So we are done with E. Then you pick D. And then you can think, can I update anything? So the only node that is left in is F, right? So I'm going to update the neighbors. So E is a neighbor, B is a neighbor, but they're already visited. They are out of set. So we are not going to touch them. And I'm going to say, okay, let me pick D and I will try to update F. Update F. So now this distance is 13 plus 2, that is 15, but F is already 14. So you do not update it, and that means we are done, right? So if you try to analyze carefully, what happened is, I'm just going to remove these edges and we'll try to highlight, right? So we'll what we will get a tree like structure, right? From A we went to B, from A we went to C also, from C we went to E, and from E we went to F. So 5, 3, 8, 8 and 6, 14, right? From B we went to D, and that's it, right? So if you look carefully, the distance of A is 0, the distance of C it's 5, the distance of E it is 8, the distance of F is 8 plus 6, 14, right? And then from A to B, this is how much? This is 4, and from B to D it is 13, right? So this is actually the shortest path to every node. Now, if someone says, okay, give me the shortest path from A to D, you know this path is going to be 13. A to F, you know this path is going to be this much, right? It is going to be 14, right? So, although I hope you're getting it, right? So, this is what this Dijkstra's algorithm is. And as we discussed, it is a greedy algorithm because it is always picking the node whose distance is minimum. So for this, we will use a data structure like set, and instead of having a queue, we will have a set like data structure from which we will be picking out these nodes, right? If you want to travel the path, what you can do, you can create one more array like distance, that will be the parent array. So for every array, whenever you are updating the distance, you can also update the parent. For example, parent of B is A, parent of C is A, parent of E is C, parent of F is E, right? So if you know the parents, you can easily backtrack and trace the path also, right? So this is how you can get the path and the distance. Now we will look at the code implementation of this algorithm. Let us talk about implementation of Dijkstra's algorithm, and I will show you what I am going to do. So I already have some boilerplate code, which is the code for creating a weighted graph. So in this weighted graph, the representation I'm using is adjacency list. Adjacency list is an array in which each object is a linked list. So there are v number of linked list. Okay. So if the graph is like this, 0 is connected with 1 and 0 is connected with 2, 1 is connected with 3, and let's say this edge is 4, this edge is 5. So in the adjacency list of 0, that means at the 0th position in the array, I am storing a linked list in which I am pushing pairs. So it is weight followed by edge. So it is 4 followed by 1. Then 0 is connected with 2. So I'm storing 5, which is the weight, followed by the node, which is 2, right? Similarly, 1 is connected with 0 and it is also connected with 3. I'm storing, okay, the weight is 4, the edge is 0, the neighbor is 0. Similarly, this is, let's say, x. I'm storing x comma 3 and so on, right? So this is how my adjacency list has been created. So to do that, I have defined a pair class in which I have two integer values, one for the node and one for the edge weight. Okay, so this distance here is representing the edge weight, right? The distance between two nodes, right? Now here we are going to build our algorithm void Dijkstras, and I'm just going to get the source node because this method I'm defining inside the graph class, so it has access to the adjacency list that is already there, right? So we don't need to pass adjacency list explicitly, right? Now before I actually write the algorithm, I would like to show you how tree set in Java works. Maybe some of you are not familiar with how to create a tree set. Okay, so tree set is a ordered set that stores data like in a sorted order, right? So let's discuss about tree set first. Let's create a tree set object. So I can say tree set, which is of the type, which is going to hold objects of the type pair weighted. So pair w is my class, and let's me call it as set. This is equal to new tree set, and I'm also going to define a lambda function so that this tree set knows that I have to sort objects according to the distance property, right? So basically in lambda function you define like this. So you have the bracket to hold the parameters. So maybe I'm going to get two pairs, pair wp1, pair wp2. Basically I'm going to define a criteria that okay, sorting should be based upon distance, and here I'm going to the return value, so that is going to be p1 dot distance minus p2 dot distance. I think we would require round brackets here like this. Now I can insert few items here, so I can say okay, s dot add maybe a new pair w, and I can give some distance. Maybe distance is 5, the node is, let's say, 11. Okay, then I can add s dot add new pair. I can set the distance is, let's say, 3, the node is 15, right? And I can say okay, s dot add new pair. So I'm just hard coding these values so that I can show you how this actually works. Then the distance is maybe 8 and the node is, let's say, 7, something like this. Now I want to remove nodes from the set in a way the node with the lowest distance is removed first. So I should be able to remove 3, then 5 and then 8, right? So how do I extract those nodes? Let's see. So while my set is not empty, what I'm going to do, I'm going to simply poll the node which is at the beginning. So I can say s out s dot poll first. So it's going to give me the pair. So I can just print the distance. That should be now in sorted order, right? So let us run our code. So I've created a main function, and this is going to be, let's say, static void, not static void Dijkstra. Let's make it public. We can call, I think there is a spelling mistake. The method I've called it as Dijkstra, not Dijkstras. So let's run this code, and what we can see, we are getting 358, right? So that means we're getting data in a sorted order. That is the expectation. So that means this is working fine, right? Okay, one more thing, just like add function, we also have a remove function in the set. I can say okay, I want to remove a pair which is, let's say, 5 comma 11, right? This is pair comma pair w. So if I go and run this code, you will see in our output we will not get 5, right? So we are getting 3 and 8 only, right? So we are getting 3 and 8, but if you give some pair which does not exist, let's say 15 comma 21, now this pair does not exist in the set, so this remove function will not do anything, right? So it's not going to throw any exception. That means we can still remove this, we can still use this, right? Now this thing I will be using while building the Dijkstra's algorithm. So I hope you have understood how do we work with tree set. So here I have defined the tree set object, here I have defined the comparator, then I added few items in the set, then I removed some items using the remove function, and then I printed. When I'm doing poll first, it is going to give me the smallest item first, and from that item I'm just printing the distance property of that item, right? So I hope all this code is clear. Now we will jump into the actual algorithm and let's see how we code it. Let's start implementing the extras. So first step would be I would create a distance array. So int distance, this is a new distance array, and I want to set everything to infinity. So I can use arrays.fill this distance array with integer dot max value. Okay, and the distance of the source node should be set to 0. So distance of source will be 0. When my set is created, my distance array is created, I can actually start doing the traversal, right? So in the beginning, what I can do, I can push my source node into my set. So I can say, okay, s dot insert, sorry, s dot add, and I can create a new pair with the distance of the source node, which is 0, and the second item will be the source node. So that is going to be source, right? While I can say, okay, my set is not empty, I want to extract this pair, right? So the pair we will get will be 0 comma source, right? So in the beginning we are going to get this pair. So I can say, okay, pair w p, this is equal to s dot poll first. Now from this pair I can extract two things. So one is my current node, which is p dot node, and one is going to be my current distance, like how much distance I need to travel to reach the current node from the source. That will be p dot distance, right? Oh, that will be actually distance of, so distance is, now you don't need to confuse here. So distance we are storing in the distance array. Okay, so p dot distance, that is fine. Okay, we have pushed, that is also fine. P dot distance can also be used, right? So right now this distance, I know it's going to be updated in the distance array, so I'm just saying distance of source node, right? Now I need to iterate on the, sorry, not source but of the current node, right? That is the distance of the current node. So basically distance is stored in two places. One is in the distance array and second is in the set. Now what I'm going to do, now suppose I removed this node 0 and it is now connected with some other nodes, right? Maybe 1, maybe 2, right? So these are right now infinity and this distance is 0. So I got this node 0 0, right? So I can say, okay, let me take this edge, and maybe this is 4. Let me take this edge and let me try to update the distance of this node, and let me try to update the distance of this node if it is getting smaller, right? So how do I get, so I can say for every pair w, that I can say, okay, p that belongs to adjacency list of current node. So I am going to iterate over the adjacency list of the current node. So I think, let me check what is the property here. The property is adjacency list, fine. So it should be fine. So let me call it as neighboring p. So the neighboring pair. So neighboring pair. Yeah, I cannot reuse the name p here. So it will be neighboring pair. So I can say, okay, the node is neighboring pair dot node, and the edge is nothing but neighboring pair dot distance, right? Now how is this adjacency list created? So it is created like this. 0 is connected with 1, which is at distance 5, which has this edge length 5 and the node is 1, and this edge length is 4 and the node is 2. So this is what is my neighboring pair. So neighboring pair is this, getting the node which is this, I'm getting the edge which is 5, right? Now you have to see that if you take this path, if you go from 0 to this node, right? Let me say this is 8. Okay, let me say this is 8. That will be better actually. Not this one. This is 8, right? So 5 comma 8, and maybe this edge is 2, right? This edge is 2. Now I will show you what is going to happen. So you are going to iterate over this. You're going to say, okay, distance of 0 plus 5, is this less than infinity? If it is less than infinity, you should update it. So you can say, okay, if the current distance, which is 0, plus the edge that you are taking, is it less than the node that you are reaching? So that node is 1. So distance of that neighbor, let me call this as neighbor only, right? So you're reaching a neighbor. If the distance of neighbor is getting minimized, you should minimize it, right? So two things I'm going to do. Now here we have two possibilities, that this node was already present in the set or this was not present in the set, right? What I'm going to do, if it is present, I will update the distance. If it is not present, I will simply add it to the set, right? Now update operation is not possible on set. So in order to do an update, I can say, okay, I will do remove plus insert, right? That is how I'm going to do it, right? So what I'm going to do, irrespective of it is present or not, I can always call the remove from the set, right? So removal can be done if even if the element is not present, nothing will happen. If it is present, it will get removed. So update, what I'm going to do, I'm going to say, okay, let's remove the old object from the set. The old object is going to be a pair, which is going to have two things. One is the distance, like the old distance. So that will be distance of the neighbor followed by the neighbor. You can remove it. Now, if it is present, it will get removed. If it is not present, nothing will happen. So we can execute this operation. Then we can update. Okay, we can calculate and the new distance. The new distance will be nothing but you can say the new distance is nothing but current distance plus edge. That is the new distance, and where it should get stored at two places. One is in the distance array. The distance of neighbor you can update in the distance array, and here you can say, okay, I have to add it to the set so that in future it can update its neighbors also. So I can say, okay, s dot add new pair where the distance is now distance of neighbor. Now this is the updated value. Look at this. This is the updated value, whereas this is the old value, right? So I've updated it and I've pushed it into the set. Fine. This looks good. If we keep on doing this, current node, I've used it here. Fine. Current distance, I used it here. Fine. This looks good. I think this is done, right? So finally, what we can do, we can print the distance array, right? So I will do the dry run. Don't worry. Print the distance array. So I can say s out arrays dot toString. If you want to return distance of some specific node, you can return that as well. But here I'm just printing the distance array. Now let's go and run this code. So I'm getting 0, 4, 5, 13, 8 and 14. I will show you the graph for which we have done this. So this is the same graph that we have taken in the example. Let's see how we are doing it, right? So we are saying in the beginning distance of source is 0. So this distance is 0 and s dot add new pair. So in my set, I have a new pair 0, 0, right? While set is not empty, I remove this node from the set. So current node is 0, current distance is 0. So for the neighbors of this node, which are this and this 1 and 2, I say, okay, neighboring node is this, fine. If I take this edge, that is 4. If it minimizes this distance, which is infinity, then I update it. So I remove a pair from the set, which is this 1 comma infinity. So this was not there, right? Infinity comma 1, it was not there. Hence nothing happens in this line, and I update the distance. So distance of neighbor. So this is my node. Okay, this is my current node. This is my neighbor, right? So I update the distance of neighbor as current distance, which is 0, plus this edge, which is 4. This distance becomes 4, and I add it to the set. So I add 1 comma 4 in the, let's say 4 comma 1. I'm putting distance first. So I add 4 comma 1 in the set, right? In the same iteration, because this for loop is running, I also update. I take this edge and I say, okay, this was infinity, and I add 5. So this distance becomes 5. So I add 5 comma 2 in the set, right? So it is sorted. So 5 will come here, right? This is gone now, right? So distance, this is gone from the set because we did poll first, right? Poll first will remove this item. Next item we will get is 4 comma 1. So we will get this, fine. We get the node, which is 1. We get the distance. We get the current distance, which is 4. Then we try to traverse the neighbors, right? So we try to cover this node, this node, this node, this node, right? Now from 1 to 0, if you go, distance will increase. So this if will not execute. From 1 to 2, if you go, again the distance will increase. So this if will not execute. But if you go from 1 to 4, this distance was infinity. So this will get updated. So this will be 4 plus 7. This will become 11. So what you will do, you will push 11 comma 4 here by taking this edge. And again, this was infinity. So you will do 4 plus 9, which is 13. So you push 13 comma 3 here, right? So this is also covered, right? Now 1 has done its job. 1 is out. Next you pop this node. So you get this node and you try to update the neighbors. If you go to 0, distance will increase. 1, if you go, distance will increase. So you take this edge, and how much you get? Now you get, okay, earlier it was 5. 5 plus 3, it is 8. So this was how much? This was 11. So this has to become 8. So what do? You remove this pair, okay, and instead of this you insert 8 comma 4, and of course this is removed. So 8 comma 4 is there. So next you will pick this pair 8 comma 4, and you will try to update the neighbors. So this will be 8 plus 13. this edge 21. Earlier distance was how much? So this distance was 13 actually, right? So it will be now 8 plus 13, which is 21. Hence you do not update here. But if you talk about this edge, so this was infinity, so it will be 8 plus 6, 14. So you insert 14 comma 5 in the set, right? So 8 is done. Then you pick this node 13 comma 3. You try to update this neighbor, which is 13 plus 13, 26. This neighbor increases, this neighbor again, this is 13 plus 2, 15, right? So again, it is not able to update any node, so you remove this. So for loop does not run for the if condition is not true for this node, right? Then you remove this again, you are not able to minimize any of the neighbors, hence this is also gone, and hence you get the final distances. Okay, so you get 14 here, so the fifth node is 14. Then you have the fourth node, which is 8, fine. Then you have third node, which is 13, yes. Then you have the second node, which is 5, yes. You have the first node, which is 4, and you have the zeroth node, which is 0. So that is the Dijkstra's algorithm for you, right? Now let us also talk about complexity in detail, right? So what about the complexity? So if you look carefully, how many times this while loop is running? So from the while loop, what we can accept that this loop is going to run how many times? Can you make any guesses? Or if you talk about these two loops together, right? The while loop and the for loop, right? So what is happening in across all the iterations? What you are doing, you are iterating over the neighbors of a node, right? So if this is node, so in the adjacency list, if I have let's say two items here, I have 3 4 5 items here, right? 6 7 8 some items here, 9 items, 10 11 12, right? So what is happening? So what is happening that in each iteration of while loop, you are iterating over neighbors of some node, right? So how many neighbors we will have? So it is basically, you can say I'm doing e iterations, right? I'm doing e iterations across all the iterations of this while loop, because we are iterating over the adjacency list, right, of some node. So across all the iterations, we are going over the adjacency list of all these nodes, right? So that means in total there are e edges. So hence there will be effective e iterations. And in each iteration, if we assume that this operation is being executed, right? So we are inserting or removing something from the set. That is not an order one operation. That is a log of set size. So how many vertices will be there in the set? So at max there will be v vertices, right? So that means in e iterations, I'm doing an operation which is going to be log v, right? So the overall complexity is going to be e log v, and that is the optimized approach for Dijkstra's algorithm, right? Because if we are getting the minimum, we're getting the minimum here also. Pole first is log v, right? And this is also log v, right? So what I'm saying, that while and for loop combined, they are doing e iterations, because you're traversing across adjacency list, okay? And there are e edges, and for each of these iterations you are doing an operation that is of log v complexity. Hence the overall complexity of this algorithm is e log v, right? And this is the optimized approach for Dijkstra's algorithm. So that was the Dijkstra's algorithm for you. I hope you understood the algorithm as well as the code. Now this problem can also be formulated in the form of a 2D matrix. Given a 2D matrix where each cell represents the cost to travel through that cell, you might be asked to compute the shortest cost from a given source, which is some cell, to some other cell in a 2D matrix. You can implement the same Dijkstra's algorithm without having an explicit graph on a 2D matrix as well. So I am sure you will try it at your own. And before you leave, make sure you like this video, hit the subscribe button, and share it with your friends. I will see you next time.